Hello, and welcome to tonight's space sleep story. Tonight we explore the Sun, our closest star. A 2-hour journey transforming familiar sunlight into cosmic understanding. The star you see almost every clear day, taken for granted like breathing, is extraordinary upon examination. An ongoing fusion explosion, converting hydrogen into helium, powering all life on Earth. Settle into comfort, close your eyes, and prepare to drift through stellar science toward peaceful rest. Before we begin, let us prepare your body and mind with gentle breathing. Take a slow, deep breath with me now. Inhale gently for 4 counts. Hold the peace. Exhale for 6. Feel your body releasing into stillness. Notice how your chest rises and falls with each breath. Your shoulders drop. Tension melts away. Another gentle breath as we continue our preparation. This time, notice how your chest rises and falls naturally, effortlessly. Breathing is automatic, like sunrise itself. Hold this peaceful moment. Feel the stress of the day leaving your body. With each breath, you release a little more into relaxation, drifting toward the calm state where learning becomes peaceful contemplation. The Sun. You have seen it almost every clear day of your life. Familiar as breathing, taken for granted. But consider what it truly is. The Sun is an ongoing fusion explosion 149.6 million kilometers away, converting 600 million tons of hydrogen into helium every second, releasing energy equivalent to 100 billion 1 megaton nuclear bombs detonating continuously, producing 65 billion neutrinos passing through each square centimeter of your body this moment. The familiar becomes extraordinary. Perhaps you stand at a window on a cold morning, or walk outside on the shortest day of the year, December 21st, winter solstice in the northern hemisphere. The sun appears weak, distant, its light slanting through bare trees. You notice its absence more than its presence. Short days, long darkness, missing sunlight. This creates the perfect context to appreciate what the sun is, what it does, why it matters so profoundly. Tonight we understand the star you think you know, The Sun is not just there. It is 1.989 times 10 to the 30th power kilograms. 332,946 Earth masses. 99.86% of the entire solar system's mass. Composition by mass: 73.46% hydrogen, 24.85% helium, less than 2% heavier elements like oxygen, carbon, iron. It is not a ball of fire requiring oxygen. It is plasma, the fourth state of matter, ionized gas held together by gravity. Understanding begins with basic facts. The Sun's core occupies the innermost 25% of its radius, but contains 34% of its mass. Conditions there: temperature 15 million Kelvin, pressure 250 billion atmospheres, density 150 grams per cubic centimeter, 150 times the density of water. These extreme conditions enable nuclear fusion. 4 hydrogen nuclei combine through multiple steps to form one helium nucleus, converting 0.7% of mass to energy via Einstein's equation E equals mc squared. This is how stars work. Every second, the core converts 600 million tons of hydrogen into 596 million tons of helium. 4 million tons of mass converted directly to pure energy. The Sun produces 3.828 times 10 to the 26th watts total power output. Yet despite losing 4 million tons per second, the Sun has enough hydrogen fuel to continue fusion for another 5 billion years. The scale is almost incomprehensible, yet the math is precise. Steady, reliable, patient fusion. Ancient peoples recognize the Sun's importance without understanding its mechanism. Virtually all ancient civilizations venerated the Sun. Egyptian Ra, primary deity from 2600 BCE. Aztec Tonatiuh, requiring human sacrifices to sustain the Sun's journey. Greek Helios, driving his chariot across the sky. Hindu Surya. Japanese Amaterasu, sun goddess, ancestor of emperors. This was not primitive superstition, but rational recognition of dependency. Without sun, no warmth, no light, no seasons, no agriculture, no life. They understood dependency intuitively. Stonehenge, constructed around 2500 BCE, aligns precisely to summer solstice sunrise. The heel stone marks where the sun rises on the longest day. This demonstrates sophisticated solar observation by Neolithic peoples. Babylonian astronomers around 700 BCE developed eclipse prediction methods using the Saros cycle, an 18-year, 11-day pattern after which eclipses repeat. They recorded observations on cuneiform tablets, predicting future eclipses from pattern recognition alone. Empirical astronomy preceded theoretical physics by millennia. Aristarchus of Samos, around 270 BCE, attempted the first quantitative measurement of the sun's distance. He observed the moon at half phase when the angle between sun, moon, and earth was 90 degrees. He measured the angle from earth to sun at approximately 87 degrees. From this, he calculated the sun was 19 times farther than the moon. The actual ratio is about 400. His measurement had large error due to limitations of ancient instruments, but the conceptual achievement was monumental. The first attempt to measure cosmic distance. Understanding evolved slowly. The sun is not burning chemically because chemistry lacks sufficient energy to power a star for billions of years. It is not collapsing gravitationally because that would exhaust in mere millions of years. Yet geology proved Earth billions of years old. The answer came only in the 20th century. Arthur Eddington in 1920 proposed that stars are powered by nuclear fusion, transmutation of elements, hydrogen building into helium. He wrote, "Only one source has the necessary energy density to make stars shine for millions of years." Fusion was the answer. Hans Bethe, a German-American physicist, solved the detailed mechanism in 1938. He later recounted working out the proton-proton chain reaction during a train ride from Washington to Cornell. By the time he arrived, he had calculated how hydrogen fuses to helium in stellar cores, step by step. The mathematics matched observations perfectly. For this work, he received the 1967 Nobel Prize in Physics. We finally understood how the sun has shone for 4.6 billion years and will continue for 5 billion more. Nature's engineering is elegant. Let us journey from the sun's surface inward, layer by layer, building understanding. What you see when you look at the sun, safely through filters or indirectly, is the photosphere. The photosphere is the visible surface, a thin layer about 500 kilometers thick, where the sun becomes opaque to visible light. Temperature: 5,778 Kelvin, appearing yellow-white to human eyes. It is not a solid surface. The sun is entirely plasma. The photosphere is simply where light can finally escape after its long journey from the core. This is what we call the Sun's surface. Look closely at high-resolution images of the photosphere, and you see granulation, a mottled pattern like cobblestones. Each granule is approximately 1,000 kilometers across and lasts 8 to 20 minutes. These are the tops of convection cells. Hot plasma rises in the bright centers, cools, then sinks at the dark boundaries. The entire visible surface is in constant churning motion. Limb darkening occurs at the sun's edge because your viewing angle sees cooler, higher layers. The sun's surface reveals the convection beneath. Sunspots appear as dark regions on the photosphere, but they are dark only by contrast. A typical sunspot has a temperature of 3,800 to 4,200 Kelvin, about 1,500 degrees cooler than the surrounding photosphere. If you could isolate a sunspot, it would glow bright orange. Sunspots form where strong magnetic fields, 3,000 to 4,000 Gauss, 10,000 times stronger than Earth's surface field, suppress convection and reduce heat flow. Typical sunspot diameter, 10,000 to 50,000 kilometers. Earth is 12,742 kilometers across. Many sunspots are larger than our entire planet. Galileo Galilei in 1612 used his telescope to observe dark spots on the sun's disk. He documented their motion across the surface, which demonstrated that the sun rotates. This challenged Aristotelian doctrine of the sun's perfection. Galileo published Letters on Sunspots, describing his observations. He worked independently alongside German astronomer Johannes Fabricius and Englishman Thomas Harriot, who also observed sunspots around the same time. The telescope revealed that even the sun has blemishes, that perfection was a philosophical idea, not a natural law. Above the photosphere lies the chromosphere, a thin reddish layer about 2,000 to 3,000 kilometers thick. It is visible during total solar eclipses as a thin ring of color, just as the moon covers the sun's disk. The name means color sphere in Greek. Something strange happens in the chromosphere. Temperature increases from 5,800 Kelvin at the top of the photosphere to 20,000 Kelvin at the top of the chromosphere, despite moving away from the heat source. This temperature inversion puzzled scientists for decades. The chromosphere contains spicules, jet-like structures 500 kilometers wide, 10,000 kilometers tall, lasting 5 to 10 minutes. The sun's atmosphere is dynamic. Beyond the chromosphere lies the corona, the outermost atmosphere extending millions of kilometers into space. During total solar eclipses, when the moon blocks the bright photosphere, the corona becomes visible as a pearly white halo with delicate streamers. The corona's temperature reaches 1 to 3 million Kelvin, far hotter than the surface below it. How can the atmosphere be hotter than the surface when you are moving away from the fusion core? This coronal heating problem remains incompletely understood. Leading theories involve magnetic reconnection and wave heating, but observations are difficult. The corona is 1 trillion times less dense than sea-level air on Earth. Hot but tenuous. The solar wind originates in the corona. This is a continuous stream of charged particles, protons and electrons, escaping into space. Typical speed ranges from 400 kilometers per second for slow wind to 750 kilometers per second for fast wind. The Sun loses approximately 1 million tons of material per second to the solar wind. This wind extends throughout the solar system, creating a bubble called the heliosphere. When the solar wind interacts with Earth's magnetosphere, it can trigger auroras. As we explored in episode 22, the solar wind connects Sun to planets. Below the visible surface lies the convection zone, the outer 30% of the Sun's radius. Here, energy is transported by convection, hot plasma rising and cool plasma sinking in continuous circulation. Temperature ranges from 2 million Kelvin at the base to 5,800 Kelvin at the photosphere. The convection zone contains cells of various sizes. Granules are about 1,000 kilometers across, with turnover times of minutes. Supergranules are 30,000 kilometers across, lasting about 1 day. Giant cells may be 200,000 kilometers across, persisting for months. It is a churning, turbulent region, constantly in motion. Below the convection zone, from 0.25 to 0.7 solar radii, lies the radiative zone. Here, energy transport occurs via radiation. Photons are absorbed and re-emitted countless times, bouncing randomly through the dense plasma. Temperature drops from 7 million Kelvin at the inner boundary to 2 million Kelvin at the outer boundary. Density decreases from 20 grams per cubic centimeter to 0.2. The radiative zone is extremely stable, with minimal turbulence. But the photon's random walk is so tortuous that it takes 10,000 to 170,000 years for energy to traverse this zone. Light born in the core takes millennia to reach the surface. Between the radiative zone and convection zone lies the tachocline, a narrow transition region about 5% of the solar radius thick. It is located at 0.7 solar radii. The radiative zone rotates as a solid body, all latitudes turning together. The convection zone exhibits differential rotation. The equator rotates in 25 days, the poles in 36 days. This shear at the tachocline generates the Sun's magnetic field through dynamo action. Poloidal magnetic field converts to toroidal field here. The tachocline is critical for understanding the 11-year solar cycle. A thin layer with profound effects. And at the center, the core. The innermost 25% of the Sun's radius, containing 34% of its mass, concentrated in just 1.5% of its volume. Conditions are extreme beyond human experience. Temperature, 15 million Kelvin. Pressure, 250 billion atmospheres, 250 billion times Earth's sea level pressure. Density, 150 grams per cubic centimeter. These conditions are sufficient to overcome electromagnetic repulsion between protons and enable nuclear fusion through quantum tunneling. The nuclear furnace at the Sun's heart. The proton-proton chain reaction is a multi-step process. 4 hydrogen nuclei, which are simply protons, combine through intermediate stages to form one helium nucleus consisting of 2 protons and 2 neutrons. This requires overcoming the electromagnetic repulsion between positively charged protons. Quantum tunneling allows protons to fuse at temperatures lower than classical physics would predict. The net result converts 0.7% of the initial mass into energy, according to Einstein's equation E equals mc squared. Remarkably, a single proton takes an average of 10 billion years to complete the fusion cycle from start to finish. Fusion is rare for any individual proton, but with countless protons, the total energy output is enormous. Every fusion reaction produces neutrinos, nearly massless particles that interact so weakly with matter that they pass through the entire Sun and through Earth almost without stopping. 65 billion neutrinos pass through each square centimeter of your body every second. Most come from the Sun. Neutrinos travel at nearly the speed of light. They were born in the Sun's core 8.3 minutes ago and have just reached you. Unlike photons, which take tens of thousands of years to escape the Sun, through countless absorptions and re-emissions, neutrinos escape immediately. Detecting them confirms that fusion is occurring in the core right now. Invisible messengers from the sun's heart pass through you constantly. Raymond Davis Jr. built a neutrino detector deep underground in a defunct gold mine in South Dakota. The detector contained 615 tons of cleaning fluid, tetrachloroethylene, chosen because neutrino interactions could convert chlorine atoms to argon. Starting in 1968, Davis and his team would wait months, then carefully extract and count the argon atoms produced. They found only about 1/3 the number of neutrinos predicted by solar models. This became known as the solar neutrino problem. Either the experiment was wrong, or our understanding of the sun was wrong, or physics itself was incomplete. It took 30 years to solve the solar neutrino problem. The answer: neutrinos change flavor during their 8-minute journey from Sun to Earth. There are 3 types of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. The Sun produces electron neutrinos, but they oscillate between types as they travel. Davis's detector was sensitive only to electron neutrinos, so it missed the 2/3 that had changed flavor. Other detectors sensitive to all neutrino types confirmed the total matched predictions. Davis and Japanese physicist Masatoshi Koshiba shared the 2002 Nobel Prize in Physics for pioneering neutrino astronomy. The Sun and our calculations were both correct. Neutrino physics was incomplete. The Sun follows an 11-year activity cycle, oscillating between solar minimum and solar maximum. At minimum, sunspots nearly vanish and the Sun appears quiet. At maximum, sunspot numbers peak at 100 to 200 and solar activity surges. The magnetic field reverses polarity every 11 years, so the complete magnetic cycle is actually 22 years. Solar cycle 25 began in December 2019 and will reach maximum around 2024 to 2025. The cycle affects aurora frequency, satellite operations, and space weather forecasting. The Sun breathes in and out over decades, a rhythm within rhythms. Solar flares are sudden, explosive releases of magnetic energy in active regions of the Sun. They are classified by X-ray intensity using letters B, C, M, X, with each class 10 times stronger than the previous. The largest flares release 6 times 10 to the 25th joules, equivalent to billions of hydrogen bombs. Flares produce radiation across the electromagnetic spectrum, from radio waves to gamma rays. The energy reaches Earth at the speed of light, arriving in 8.3 minutes. Flares can disrupt radio communications and damage satellites. The Sun occasionally erupts with tremendous power, yet Earth's atmosphere and magnetosphere protect us. On September 1st, 1859, British astronomer Richard Carrington was observing sunspots when he witnessed something unprecedented. He later wrote, "I was counting sunspots when two brilliant beads of white light appeared, intensifying rapidly. In 5 minutes, they vanished. I rushed to find someone to confirm I was not imagining it. That night, brilliant red auroras appeared visible even in tropical latitudes." Carrington wondered, could the sun have caused them? The timing suggested a connection, though the mechanism was unknown at the time. This became known as the Carrington event, the most powerful geomagnetic storm in recorded history. It established the Sun-Earth connection. Coronal mass ejections, CMEs, are massive eruptions of plasma and magnetic field from the Sun's corona. They release 10 to 100 billion tons of material, traveling at 250 to 3,000 kilometers per second. Travel time to Earth ranges from 15 hours for the fastest to 4 days for typical events. CMEs carry an embedded magnetic field. When this field reconnects with Earth's magnetosphere, it can trigger geomagnetic storms and brilliant auroras, as we explored in episode 22. During solar maximum, CMEs occur about once per day. During solar minimum, they are rare. The Sun exhales plasma clouds into space regularly. Prominences and filaments are large-scale structures of dense plasma suspended in the corona by magnetic fields. When seen at the Sun's edge during eclipses, they appear as bright loops or arcs called prominences. When seen on the solar disk, they appear as dark ribbons called filaments. They can extend 100,000 kilometers or more above the surface. Prominences remain stable for days or weeks, held aloft by magnetic tension. Sometimes they erupt suddenly, contributing to coronal mass ejections. Temperature ranges from 8,000 to 15,000 Kelvin, cooler than the surrounding corona. Plasma trapped in magnetic loops, glowing pink against the darkness of space. Coronal holes are large, dark regions in the corona where magnetic field lines open into space rather than looping back to the surface. They appear dark in X-ray and ultraviolet images because they are cooler and less dense than surrounding regions. Coronal holes allow high-speed solar wind to escape at 750 kilometers per second, compared to 400 from closed regions. They are long-lived features, persisting for months. Often located at the solar poles during solar minimum, they can expand to mid-latitudes during maximum. Fast solar wind streams from coronal holes can trigger recurrent aurora displays when they sweep past Earth every 27 days as the Sun rotates. Open magnetic field lines create highways for solar wind to escape. The Sun is a G2V star in the spectral classification system. G2 indicates a surface temperature of approximately 5,800 Kelvin, giving it a yellow-white color. V indicates main sequence, a hydrogen-fusing dwarf star. The Sun is about halfway through its 10 billion year main sequence lifetime. It is unremarkable cosmically, 8 times more massive than the smallest red dwarfs, 1/8 the mass of the largest main sequence stars. Mid-sized, average, one among hundreds of billions of similar stars in the Milky Way galaxy. Yet to us, it is everything. Our star, our life giver, the center of our world. The Sun vibrates. Millions of oscillation modes with periods ranging from 3 to 12 minutes, caused by sound waves trapped inside the Sun. These acoustic waves bounce between the photosphere and various depths within the interior. By analyzing the frequencies and patterns of these vibrations, scientists can probe the Sun's internal structure. This technique is called helioseismology, analogous to how seismology reveals Earth's interior through earthquake waves. Helioseismology confirmed the depth of the convection zone, the rotation profile at different depths, and properties of the core. The Sun's music reveals its secrets. The Sun's total irradiance, the amount of energy reaching the top of Earth's atmosphere, varies slightly over the 11-year solar cycle by about 0.1%. Sunspots slightly decrease output because they are cooler regions. But faculae and plages, bright regions associated with magnetic activity, slightly increase output. The net effect is that the Sun is slightly brighter during solar maximum, despite having more sunspots. This affects Earth's climate on a small but measurable scale. Satellites have monitored solar irradiance continuously since 1978. The Sun is remarkably stable, varying by less than 1 part per thousand over years. Between 1645 and 1715, a period known as the Maunder Minimum, sunspots nearly vanished. Observers recorded very few sunspots for 70 years. This coincided with the Little Ice Age in Europe, when winters were particularly harsh. The correlation suggests that solar activity may affect Earth's climate, though the mechanism is debated. The Maunder minimum demonstrates that the solar cycle is not perfectly regular. It can pause or weaken. The current solar cycle 25 appears to be progressing normally. Even the Sun has moods, variations across centuries. Space weather forecasting monitors the Sun for Earth-directed CMEs and flares. Satellites like SOHO, Stereo, and SDO provide continuous observation. Coronagraphs detect CMEs. X-ray sensors detect flares. Models predict CME arrival time at Earth. NOAA Space Weather Prediction Center issues forecasts and warnings. This is critical for protecting satellites, astronauts, power grids, and GPS systems. We watch the Sun to stay safe. Parker Solar Probe, launched in August 2018, makes the closest approaches to the Sun ever attempted by humanity. Perihelion at 6.9 million kilometers from the surface, inside the corona itself. The heat shield withstands 1,377 degrees Celsius, while instruments remain at room temperature. The spacecraft travels at 192 kilometers per second, the fastest human-made object ever created. Touching the Sun, answering questions humanity has asked for generations. The photosphere is what we see when we look at the Sun safely. This visible surface averages 5,778 Kelvin, appearing yellow-white to human eyes. It's actually a thin layer only 500 kilometers thick, where the Sun becomes opaque to visible light. Not a solid surface, but the boundary where plasma density becomes high enough to trap photons. The photosphere shows granulation patterns. Hot plasma rises from below, creating bright cell centers. Cool plasma sinks, forming dark boundaries. Each granule spans about 1,000 kilometers across and lasts 8 to 20 minutes. Watching the Sun's surface through proper filters reveals this constant churning motion, like boiling water magnified to planetary scale. Sunspots appear as dark regions on the photosphere. They're actually 3,800 to 4,200 Kelvin, still glowing intensely hot. They appear dark only by contrast with the surrounding 5,800 Kelvin surface. Strong magnetic fields, 3,000 to 4,000 Gauss, suppress convection in these regions, reducing heat transport and creating cooler zones. Galileo first observed sunspots telescopically in 1612. He watched dark spots move daily across the sun's disk, demonstrating solar rotation. This simple observation challenged the Aristotelian doctrine of the sun's perfection. The sun had features, variations, changes. It wasn't an unblemished celestial sphere, but a dynamic, active star. Above the photosphere lies the chromosphere. This reddish layer spans 2,000 to 3,000 kilometers thick, visible only during total solar eclipses. Temperature unexpectedly increases from 5,800 Kelvin at the top of the photosphere to 20,000 Kelvin at the chromosphere's upper boundary. Despite moving away from the heat source, it gets hotter. This temperature inversion puzzled scientists for decades. How can the atmosphere get hotter as you move farther from the fusion core? The answer involves magnetic field energy and wave heating, processes still being studied with spacecraft like Parker Solar Probe. The chromosphere contains spicules, jet-like structures 10,000 kilometers tall, lasting 5 to 10 minutes. Beyond the chromosphere stretches the corona. The sun's outermost atmosphere extends millions of kilometers into space. Here, temperatures reach 1 to 3 million Kelvin, vastly hotter than the 5,800 Kelvin surface below. The coronal heating mechanism remains one of solar physics' deepest mysteries. Magnetic reconnection and wave heating are leading theories. During total solar eclipses, the corona becomes visible. When the moon perfectly covers the photosphere, the corona emerges as a pearly white halo. Annie Jump Cannon observed the 1925 eclipse. Pearly white halo extending millions of kilometers, streamers flowing outward. In 2 minutes 40 seconds of totality, we captured the sun's hidden atmosphere. Every eclipse reveals new coronal details. Now let's journey inward from the visible surface. Below the photosphere lies the convection zone, the outer 30% of the sun's radius. Here, energy transport occurs through convection, hot plasma rising and cool plasma sinking. Temperature ranges from 2 million Kelvin at the base to 5,800 Kelvin at the top. Convection cells exist in various sizes. Small granules, 1,000 kilometers across, turn over in 8 to 20 minutes. Supergranules, 30,000 kilometers across, last about 1 day. Giant cells, 200,000 kilometers across, persist for months. The convection zone is constantly churning, transporting energy from deep interior toward surface. Beneath the convection zone lies the radiative zone. This region extends from 0.25 solar radius at the core boundary to 0.7 solar radius. Energy transport occurs via radiation, photons absorbed and re-emitted billions of times. Temperature drops from 7 million Kelvin at the inner boundary to 2 million Kelvin at the outer edge. The radiative zone is extremely stable. Minimal turbulence, smooth energy flow. Photons undergo a random walk, absorbed and re-emitted by ions and electrons constantly. This prolongs their journey from core to surface, taking 10,000 to 170,000 years, despite the zone being only a few 100,000 kilometers thick. Between the radiative zone and convection zone lies the tachocline. This narrow boundary layer, only about 5% of the solar radius thick, is critically important. The radiative zone below rotates as a solid body, same rate everywhere. The convection zone above exhibits differential rotation, 25 days at the equator, 36 days at the poles. The shear between these rotation patterns generates the Sun's magnetic field. Through dynamo action, the tachocline amplifies and organizes magnetic fields. Poloidal magnetic field converts to toroidal field, wrapping around the Sun. This process drives the 11-year solar cycle, sunspot formation, flares, and coronal mass ejections. The tachocline is the Sun's magnetic engine. Finally, we reach the core, the innermost 25% of the Sun's radius, containing 34% of its mass, concentrated in just 1.5% of its volume. Here, conditions become extreme beyond human experience. Temperature 15 million Kelvin. Pressure 250 billion atmospheres. Density 150 grams per cubic centimeter. These conditions enable nuclear fusion. 4 hydrogen nuclei, protons, combine through multiple steps to form one helium nucleus. The process requires overcoming electromagnetic repulsion, protons repelling each other because they're positively charged. Quantum tunneling allows fusion despite this barrier. The result converts 0.7% of mass directly to energy via Einstein's equation E equals mc squared. The Sun converts 600 million tons of hydrogen into 596 million tons of helium every second. 4 million tons of mass become pure energy. This produces 3.828 times 10 to the 26th watts total power output, equivalent to 100 billion 1 megaton nuclear bombs detonating every single second, continuously, for billions of years. Bethe solved this mechanism in 1938. On the train from Washington to Cornell, I worked out the detailed proton-proton chain reaction. By arrival, I'd calculated how hydrogen fuses to helium in stellar cores. We finally understood how the Sun has shone for billions of years and will continue billions more. Nature's engineering is elegant. Every fusion reaction produces neutrinos. These nearly massless particles interact so weakly they pass through ordinary matter almost as if it weren't there. 65 billion neutrinos pass through each square centimeter of your body every second. Most come from the Sun, created 8 minutes 20 seconds ago in the core. They travelled through the entire Sun and across space to Earth without stopping. Neutrino detection confirms fusion occurring in the Sun's core. Raymond Davis Jr. built a detector 1 mile underground in a defunct South Dakota gold mine. 615 tons of cleaning fluid to catch neutrinos from the Sun. Every few months, a few dozen argon atoms appeared, produced by neutrino interactions. But he detected only 1/3 the predicted number. Either our experiment was wrong, or our understanding of the Sun was wrong, or physics was incomplete, Davis reflected. It took 30 years to solve. Neutrinos change flavor during their 8-minute journey from Sun to Earth. The deficit wasn't error, it was discovery. Davis shared the 2002 Nobel Prize for opening neutrino astronomy. The Sun follows an 11-year activity cycle. Sunspot number varies from nearly 0 at minimum to 100 to 200 at maximum. Magnetic field polarity reverses every cycle, making the complete magnetic cycle 22 years. Solar Cycle 25 began December 2019 and will peak around 2024 to 25. Solar flares release magnetic energy explosively. Sudden brightenings in active regions, classified by X-ray intensity B, C, M, X classes, each 10 times stronger than the previous. The largest flares release 6 times 10 to the 25th joules, equivalent to billions of hydrogen bombs. They produce radiation across the electromagnetic spectrum, from radio waves to gamma rays. Energy reaches Earth at light speed in 8.3 minutes. Richard Carrington witnessed the first recorded solar flare, September 1st, 1859. I was counting sunspots when two brilliant beads of white light appeared, intensifying rapidly. In 5 minutes, they vanished. I rushed to find someone to confirm I wasn't imagining it. That night, brilliant red auroras appeared. Could the sun have caused them? The Carrington event established the Sun-Earth connection. Coronal mass ejections erupt massive clouds of plasma and magnetic field from the corona. 10 to 100 billion tons of material launched at 250 to 3,000 kilometers per second. Travel time to Earth ranges from 15 hours for the fastest to 4 days for typical events. They carry embedded magnetic fields, enabling reconnection with Earth's magnetosphere. When CMEs reach Earth, they trigger geomagnetic storms and auroras. As we explored in episode 22, solar wind creates the auroras. Now you understand where that solar wind originates, how it's generated, why coronal mass ejections are so powerful. CMEs occur about once per day during solar maximum, becoming rare during minimum. Prominences are large-scale structures of dense plasma suspended in the corona by magnetic fields. When viewed at the sun's edge during eclipses, they appear as bright loops extending upward. On the sun's disk, the same structures appear as dark ribbons called filaments. They can extend 100,000 kilometers or more above the surface. Some remain stable for days or weeks before eventually erupting and causing CMEs. Coronal holes are large, dark regions in the corona with open magnetic field lines. These areas allow high-speed solar wind to escape, 750 kilometers per second versus 400 from closed regions. Long-lived features persisting for months, often located at solar poles during minimum, expanding to mid-latitudes during maximum. They're the source of fast solar wind streams that trigger recurrent aurora displays. The Sun contains 1.989 times 10 to the 30th kilograms. 332,946 Earth masses. 99.86% of the entire solar system's total mass. Composition by mass: 73.46% hydrogen, 24.85% helium, 0.77% oxygen, 0.29% carbon, 0.16% iron. Trace amounts of other elements. The Sun loses 4 million tons per second to energy conversion. Mass becoming energy via Einstein's equation. Yet despite this continuous loss, the Sun will remain a main sequence star for 5 billion more years. It has enough hydrogen fuel to continue its patient work, fusing atoms, radiating energy, powering life on Earth for eons to come. The Sun's radius measures 696,000 kilometers, 109 times Earth's radius. Volume could contain 1.3 million Earths, yet average density is only 1.408 grams per cubic centimeter. About 1.4 times water, less than Earth's 5.51 grams per cubic centimeter. The Sun is mostly empty space between atomic nuclei. Differential rotation occurs because the Sun is gaseous plasma, not a solid body. Equatorial rotation period, 25 days. Polar rotation period, 36 days. Different latitudes rotate at different rates, creating the shear that amplifies magnetic fields in the tachocline. This differential rotation drives the solar dynamo, the engine of solar activity. The Sun's total luminosity measures 3.828 times 10 to the 26th watts. Of this enormous output, Earth intercepts 1,361 watts per square meter at the top of our atmosphere. This is called the solar constant. Earth receives only 2.2 billionths of the Sun's total output, yet it powers the entire biosphere. Solar luminosity has increased 30% since the Sun formed 4.6 billion years ago. This is the faint young Sun paradox. How did early Earth avoid freezing when the Sun was dimmer? Stronger greenhouse gases likely compensated. As the Sun gradually brightens over its main sequence lifetime, Earth's climate must adjust. The Sun orbits Earth at a mean distance of 149.6 million kilometers. This defines one astronomical unit. Distance varies from 147.1 million kilometers at perihelion in early January to 152.1 million kilometers at aphelion in early July. A slightly elliptical orbit, 5 million kilometers difference. The Sun's angular diameter averages 0.53 degrees, roughly the same as the Moon by remarkable coincidence. This enables total solar eclipses where the Moon perfectly covers the photosphere, revealing the corona. Light travel time from Sun to Earth, 8 minutes 20 seconds. We see the Sun as it was 8.3 minutes ago. The Sun is classified as a G2V star. G2 indicates surface temperature around 5,800 Kelvin, producing yellow-white color. V indicates main sequence, a hydrogen-fusing dwarf star. The Sun is about halfway through its 10 billion year main sequence lifetime. An unremarkable mid-sized star, 8 times more massive than red dwarfs, 1/8 the mass of the largest main sequence stars. The Sun vibrates with millions of oscillation modes, periods ranging from 3 to 12 minutes, caused by sound waves, acoustic modes, trapped inside the Sun. Analyzing these vibrations reveals internal structure, like seismology reveals Earth's interior. This technique, called helioseismology, confirmed the convection zone depth, rotation profile, and core properties. Total solar irradiance varies by about 0.1% over the 11-year cycle. Sunspots slightly decrease output because they're cooler regions, but faculae and plages, bright regions around active areas, slightly increase output. The net effect is increased output during solar maximum, despite more sunspots. This affects Earth's climate on a small but measurable scale. Satellite monitoring began 1978. The Maunder minimum occurred from 1645 to 1715. Sunspots nearly vanished for 70 years. This period coincided with the Little Ice Age in Europe. The correlation suggests solar activity affects climate, though the mechanism is still debated. It demonstrates the solar cycle is not perfectly regular and can pause or weaken. The Sun continues its patient work. Core fusing hydrogen at 15 million Kelvin. 4 million tons converted to pure energy. Rest and enjoy the warm glow. protons begin their 100,000-year journey outward. Random walk through radiative zone, each interaction prolonging escape. Neutrinos pass through your body this moment. 65 billion per square centimetre every second. Born in the core 8 minutes ago. Solar wind flows outward at 400 kilometers per second. Invisible stream of charged particles, creating heliosphere around all planets. Magnetic fields loop and reconnect across the photosphere. Energy building in active regions, releasing occasionally in brilliant flares. The corona extends millions of kilometers into space. 1 million Kelvin despite distance from core. Coronal heating puzzle persists. Sunspots mark regions where magnetic fields suppress convection. 3000 Gauss field strength, dark only by contrast. The 11-year solar cycle continues. Magnetic polarity reverses every cycle. Solar maximum approaching 2025. Earth orbits in the Goldilocks zone, 149.6 million kilometers. Perfect distance for liquid water. Seasonal cycles result from Earth's 23.5-degree tilt. Same sun, different geometry. Summer will return. Tomorrow, the sun will rise. Earth rotates you back into sunlight, guaranteed by orbital mechanics. Ancient cultures worshipped the sun across every civilization. Egyptian Ra, Aztec Tonatiuh, Greek Helios. Recognizing dependency. Modern science reveals the mechanism. Nuclear fusion, proton-proton chain, mass to energy. Understanding deepens appreciation. has fused hydrogen for 4.6 billion years. Will continue 5 billion more. Steady, reliable, patient. Life on Earth depends entirely on this fusion reactor. Photosynthesis, weather, seasons, warmth, light, all powered by the sun. Rest now under your star's reliable glow. Fusion continues whether you observe or not. Sleep peacefully. The sun burns steadily through the night. Reliable sunrise tomorrow. Guaranteed. reliable sunrise tomorrow. Fusion never stops. Patient star. Hydrogen to helium, mass to energy. Core continues its work. 15 million Kelvin. Photosphere radiates peacefully. 5,778 Kelvin. Corona streams outward. Solar wind flows. orbits safely. Perfect distance. Seasons cycle endlessly. Tilt brings summer. Tomorrow brings light. Sunrise returns.